This week we are going to start a new chapter called product architecture, and I feel specifically for our community this would be an interesting read for us, and how the architecture of the product plays a big role. And for our community, mostly academic people, uh, creating a bigger plan for our research project also to some extent related to the product architecture, like the product that we conceive to be formed from the research, if not the directly but indirectly in future, something like that. So I thought it would be an interesting read. So yeah, let's start then. So starting with the word architecture, we get the idea that basically it talks about the macro feature of the product that are being developed. And so the general question is, how would the architecture of the product impact their ability to offer product variety? So for a company perspective, they don't want to develop every new product from the scratch, so they want to start with something, and 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 the development process must have some quality, that the same research can be used to portray different product, generating variety of products. So how to do that? That's the question that we deal with in architecture phase. Again, this is an executive phase where we need to be conscious about all the previous thing that we have done, and now on top of that we build some more exercise and try to think more in more detail in a very structured way, in a certain particular way, and that's the term here is architecture here. So, and the second question that one needs to answer is, what would be the cost implication of different product architectures? So that's also very much cost of the product also depends on a lot of other factors, and architecture is a part of it, of course. How would the architecture of the product impact their ability to complete the design within 12 months? So in a lot of companies, they have to compete with the competitor other companies in the market, and they need to design the product, or the generic product has to be something that that a new feature can be added easily, without doing a lot of changes, and that will need a lot of time. So time becomes important in competitive environment. How would the architecture of the product influence their ability to manage the development process? So the development process management is also very crucial, and a lot of things depends on how things are managed and how various teams are communicating with each other. And depending on the architecture of the product, the management also get changed, so that also people need to be conscious of. So the purpose of the product architecture is to define the basic physical building blocks of the product in terms of what they do and what their interfaces are to the rest of the device. Architectural decisions allow the detailed design and testing of these building blocks to be assigned to teams, individuals, and or suppliers, such that development of different portions of the product can be carried out simultaneously. So that's a very general outlook what is architecture here in to precisely means. Now for this particular video, basically we will try to understand exactly in detail what product architecture means, and specifically what are the type of architecture and what are the advantage of certain types and disadvantage of that type, similarly other. And we also want to understand why product architecture is important. Of course we discuss the questions, but to be more precise, we want to show and we want to discuss what are the implication of the architecture, and finally, now that we know that how it is important and how basically how it basically makes a lot of interesting feature in the product in a long run which was needed, how you follow a certain structured step that you have that quality in your research, so that it basically doesn't need too much of fine tuning or too much of looking back in the future phase when you want to build a new derivative product out of it, etc. So that's the thing we will be learning from this video. Now let's understand what product architecture means in much more detail first, and then we'll go into how the product architecture makes a lot of differences into the product development process and in the products that the company will be making. Okay, so a product can be thought of as a product can be thought of in both functional and physical term. The functional elements of a product are the individual operations and the transformations that contribute to the overall performance of the product. Functional elements are usually described in schematic form before they are reduced to specific technologies, components, and physical working principles. The physical element of a product are the parts, component, and sub-assemblies that ultimately implement the product's functions. The physical elements become more defined as the development process progresses. Some physical elements are dictated by the product concept and the others become defined during the detailed design phase. The physical elements of a product are typically organized into several major physical building blocks, which we call chunks. Each chunk is then made up of a collection of components that implement the functions of the product. The architecture of a product is this scheme by which the functional elements of the products are arranged into physical chunks and by which the chunks interact. Two types of architecture one can think of. One is a modular architecture, where the most modular architecture is the one in which each functional elements of the product is implemented by exactly one physical chunk and in which there are a few well-defined interactions between the chunks. Such a modular in architecture allow a design change to be made to one chunk without requiring a change to other chunks for the product to function correctly. The chunks may also be designed quite independently of one another. The opposite of a modular architecture is an integral architecture. An integral architecture basically means a product embodying an integral architecture will often be designed with the highest possible performance in mind. The implementation of functional elements may be distributed across multiple chunks. Boundaries between the chunks may be difficult to identify or may be non-existent. Many functional elements may be combined into a few physical components to optimize certain dimension of the performance. However, the modifications to any one particular component or feature may require extensive redesign of the product. So you can see that both are in different extremes, and I think it depends on the product. For example, electric bike, not electric, but I mean I think one vague example of the integral architecture would be the design of any motorbike, where you can't have different, because basically you need to ride on it and it has to be mechanically very rigid and also aerodynamics. If not, I mean, it's not a flight, of course, it's not an aeroplane, but still aerodynamics must make some sense. So that's in generally in those the motorbikes are made in the framework of integral architecture, where you see a lot of functionalities are basically distributed across various physical component. So it's not modular, it's not like so everything is connected with each other, etc., etc. It's a very vague example, but modular is let's not go into example right now, but both, what I'm trying to mean is that both architecture has their own advantage, disadvantage. For example, just to give you a glimpse here, modular architecture, basically you can outsource certain component to, let's say, a lot of people outsource their manufacturing to China, and all this thing happen nowadays more and more. And so what happens is that if those are made in China, then you can't really communicate easily with them, like, oh yeah, we are doing something like this, so your research or your product, the subsystem have to be this. That cannot be done easily. So in generally, in if you follow a modular architecture, then it becomes easy actually. So you can see these are managerial thing, but very important for any successful product. Now the one question you might ask, that when is the product architecture is defined exactly? So a product's architecture begins to emerge during the concept development. This happens informally in the sketches, function diagrams, and early prototypes of the concept development phase. Generally, the maturity of the basic product technology dictates whether the product architecture is fully defined during the concept development or during system level design. System level design is something that we will be learning in next video, hopefully. When the next product is an incremental improvement of an existing product concept, then the product architecture is defined within the product concept. Product architecture is one of the development decisions that most impacts a firm's ability to efficiently deliver high product variety. Architecture therefore becomes a central element of product concept. However, when the new product is the first of its kind, concept development is generally concerned with the basic working principle and technology on which the product will be based. In this case, the product architecture is often the initial focus of the system level design phase of the development. That means product architecture will be done mostly in the system design part. So you can see these are all depending on on your research project. Of course I'm talking in terms of the community that we are, but depending on your research project, basically you might need to think all this thing into different time sequences. Sometimes you might basically forget about the product architecture. So of course here I'm talking about, let's say you have a big research goal like 10-15 years, and I think it's a personal decision how you want to plan your bigger research goal, and a lot of times it's not possible, although you want to work on, and a lot of cases, specifically my fundamental science friends, they are not really, should not be interested in this kind of thing. But for applied science research, I think it is better to invest into your time into something that in long run it will be fruitful, in terms of even paper, in terms of maybe patent, etc. So for that, these bigger research plans are important, and in that context I think that all this learning that we are doing here will going to be important. So now we understand that when the product architecture will be defined. Now let's understand very important thing, that exactly how product architecture impacts the various feature of the future product. So decision about how to divide the product into chunks and about how much modularity to impose on architecture are tightly linked to several issues of importance to the entire enterprise. product change, product variety, component standardization, product performance, manufacturability, and product development management. These are all things that basically are hampered by or basically decided by how the product architecture is. The architecture of the product therefore is closely linked to decisions about marketing strategy, manufacturing capabilities, and product development management. Now let's understand how product architecture decides uh, how many changes we can make in the product in the future. So chunks are the physical building blocks of the product, but the architecture of the product defines how these blocks relate to function of the product. The architecture therefore also defines how the product can be changed. Modular chunks allow changes to be made to a few isolated functional elements of the product without necessarily affecting the design of the other chunks. Now, why do you want to make a change of the product? Or why do you want to build this capability in your research, that in future you can make change, and making it more modular, you can make change. Why you want to do that? The thing is, first is upgrade. As the technological capabilities or the user needs evolve, some products can accommodate with this evolution through upgrades. Example include changing the processor board of in a computer printer, or replacing a pump in a cooling system with a more powerful model. Second is add-ons. Many products are sold by a manufacturer as a basic unit to which the user adds components, often produced by third parties as needed. This type of change is common in personal computer industry. For example, third-party mass storage device may be added to a basic computer. Third is adaptation. Some long-lived products may be used in several different use environments requiring adaptation. For example, machine tools may need to be converted from 220 volt to 110 volt power. Some engines can be converted from a gasoline to a propane fuel supply. Fourth is wear. Physical elements of a product may deteriorate with use, necessitating replacement of the worn or owned component to extend the useful life of the product. For example, many razor allow dull blades to be replaced. Tires on vehicles can usually be replaced. Most rotational bearings can be replaced, and many appliance motors can be replaced. Next is consumption. Some products consume material which can then be easily replenished. For example, copier and printer frequently contain printer cartridge. Cameras take film cartridge. Glue guns consume glue sticks. Torches have gas cartridge, and watches contain batteries, all of which are generally replaceable. Flexibility in use. Some products can be configured by the user to provide different capabilities. For example, many cameras can be used with different lens and flash option. Some boats can be used with several warning option. Fishing rods may be accommodate several rod reel configuration. Finally, reuse. In creating subsequent products, the firm may wish to change only a few functional elements while retaining the rest of the product intact. For example, consumer electronics manufacturers may wish to update a product line by changing only the user interface and enclosure while retaining the inner workings from a previous model. So in each of these cases, a modular architecture allows the firm to minimize the physical changes required to achieve a functional change. So we can see that if your future product, or all the human resources that you're using and all the money that you are going through, going for the research and all this thing, if you think that what will come out, it will be in future needed for the products will be changed little bit here and there, so then the modular architecture is important, and that will give you the product change capability, which will basically going to have this upgradable capability, add-on capability, adaptation, where consumption, flexibility in use, reuse, these capabilities. Now, other thing that is affected is product variety. Variety refers to the range of product models the firm can produce within a particular time period in response to market demand. Products built around modular product architecture can be more easily varied without adding tremendous complexity to the manufacturing system. Next thing that is affected by product architecture is component standardization. So component standardization is the use of this same component or chunk in multiple products. If a chunk implements only one or a few widely useful functional elements, then the chunk can be standardized and used in several different products. Such standardization allows the firm to manufacture the chunk in higher volumes than would otherwise be possible. This in turn may lead to lower cost and increased quality. Next is product performance. So product architecture decides product performance. So we define product performance as how well a product implements in its intended functions. Typical product performance characteristics are speed, efficiency, life, accuracy, and noise. And integral architecture facilitates the optimization of the holistic performance characteristics and those that are driven by size, shape, mass of a product. So here you can see, so this here it comes the design of a motorbike, where I said that you need an integral architecture. So basically, depending on what exactly the product is and how you want to market it in future, basically through that, that will decide basically what kind of architecture, whether it is modular, whether it is a integral architecture. So that will decide that. An integral architecture allows for redundancy to be eliminated through function sharing, as in the case of motorcycle, and allows for geometric nesting of component to minimize the volume of a product occupies. So you can't have a very bulky bike, so it has to be of some reasonable dimension that it can the main purpose that you need to ride on it, and it must go fast, etc. So yeah, such function sharing and nesting also allows material use to be minimized, potentially reducing the cost of manufacturing the product. Next is manufacturability. So that I think we can discuss. Let's discuss this also. In addition to the cost implication of the product variety and component standardization described above, the product architecture also directly affects the ability of the team to design each chunk to be produced at low cost. One important design for manufacturing strategy involves the minimization of the number of parts in a product through component integration. However, to maintain a given architecture, the integration of the physical components can only be easily considered within each of the chunks. Component integration across several chunks is difficult, if not impossible, and would alter the architecture dramatically. Because the product architecture constrains subsequent detailed design decision in this way, the team must consider the manufacturing implications of the architecture. For this reason, DFM, that means design for manufacturing, begins during the system level design phase while the layout of the chunks is being planned. So here we will go into this in more detail in later weeks, hopefully maybe somewhere down the line we will be reading about it, which is basically chapter 13 of the book called Design for Manufacturing. Finally, uh, finally, the something that one might not expect, and that is product development management. How that is also basically is affected by the what kind of architecture we are dealing with. If a functional detail element is implemented by two or more chunks, as in some integral architecture, detailed design will require close coordination among different groups. This coordination is likely to be substantially more involved and challenging than the limited coordination required among groups designing different chunks in a modular design. For this reason, teams relying on outside supplier or on a geographically dispersed team often opt for a modular architecture in which development responsibilities can be split according to the chunk boundaries. So here we understand that how depending on the product architecture, management also uh, needed to be different actually. So here of course it's not like product architecture benefits the management, but like depending on the product architecture, the management had to be in certain way, that's what we are discussing. So yeah, now we will try to understand what kind of structured step one can take to make sure that you have a good product architecture. So because the product architecture will have profound implication for the subsequent product development activities and for the manufacturing and the marketing of the completed product, it should be established in a cross-sectional fashion effort by the development team. The end result of this activity is an approximate geometric layout of the product, description of the major chunks, and the documentation of the key interaction among the chunks. The steps are: first step is create a schematic of the product. A schematic is a diagram representing team's understanding of the constituent elements of the product. At the end of the concept development phase, some of the elements in the schematic are physical concepts such as the front in and front out paper path. So here we are talking about the example that we are dealing with, which is a printer. Some of the elements corresponding to critical components such as the print cartridge the team expect to use. However, some of the elements remain described only functionally. These are the functional elements of the product that have not yet been reduced to physical concept or the components. The schematic should reflect the team's best understanding of the state of the product, but it does not have to contain every imaginable detail such as let's forget that. These and other more detailed functional elements are described in later step. A good rule of thumb is to aim for fewer than 30 elements in the schematic for the purpose of the establishing the product architecture. For the purpose of the product establishing product architecture. If the product is a complex system involving hundreds of functional elements, then it is useful to omit some of the minor ones and to group some other into higher level functions to be decomposed later. So that is the step 1. So in step 1 you just create a schematic of the product where you don't have to be very careful about the detail, but you try to basically divide the product or the future product into some various elements. The second step is cluster the elements of this schematic. Now you have to build the relation between them. That means specifically which one is related to which one, so you group them. The challenge of step 2 is to assign each of the elements of the schematic to a chunk. At one extreme, each element could be assigned to one chunk. At the other extreme, the team could decide that the product would have only one major chunk and then attempt to physically integrate all of the elements of the product. One procedure for managing the complexity of the alternative is to begin with the assumption that each element of the schematic will be assigned to its own chunk, and then to successfully cluster elements where advantageous. To determine when there are advantages to clustering, consider these factors, which echo the implications discussed in the previous section. First factor is geometric integration and precision. Assigning elements to the same chunk allows a single individual group to control the physical relationships among the elements. Elements requiring precise location or close geometric integration can often be best designed if they are part of the same chunk. For the DeskJet printer, this would suggest clustering the elements associated with the positioning of the cartridge in x-axis and positioning the paper in y-axis. So these are technical detail. Second factor is function sharing. When a single physical component can implement several functional elements of the product, these functional elements are best clustered together. Third is capabilities of vendors. A trusted vendor may have specific capabilities related to a project, and to best take advantage of such capabilities, a team may choose to cluster those elements about which the vendor has expertise into one chunk. In the case of a DeskJet printer, an internal team did the majority of the engineering design work, and so this was not a major consideration. Next factor is similarity of design and production technology. When two or more functional elements are likely to be implemented using the same design and/or production technology, then incorporating these elements into the same chunk may allow for more economical design and/or production. A common strategy, for example, is to combine all functions that are likely to involve electronics in the same chunk. This allows the possibility of implementing all of these functions with a single circuit board. Localization of change. When a team anticipates a great deal of change in some element, it makes sense to isolate the element into its own modular chunk, so that accurate changes to the element can be carried out without disrupting any of the other chunks. Next is accommodating variety. Elements should be clustered together to enable the firm to vary the product in a way that will have value for the customer. The printer was to be sold around the world in regions with different electrical power standard. As a result, the team created a separate chunk for the element associated with supplying DC power. Next is enabling standardization. If a set of elements will be useful in other products, they should be clustered together into single chunk. This allows the physical element of the chunk to be produced in higher quantities. Next is portability of the interface. Some interactions are easily transmitted over large distances. For example, electrical signals are much more portable than the mechanical forces and motions. As a result, elements with electronic interactions can be easily separated from one another. This is also true, but to a lesser extent for fluid connections. The flexibility of electrical interactions allow the Hewlett-Packard team, that means the particular product that we are taking as an example for in this chapter, to cluster the control and the communication function into the same chunk. Conversely, the elements related to paper handling are much more geometrically constrained by their necessary mechanical interactions. So that's about step 2, which is about clustering the elements of the schematic from this schematic. Depending on various factors, starting with geometric integration and precision, function sharing, capability of vendors, similarity design and production technology, location of change, accommodating variety, enabling standardization, portability of the interfaces. Now, third step in the process of making a good product architecture is create a rough geometric layout. So a geometric layout can be created in 2 or 3 dimensions using drawings, computer models, or physical models. Creating a geometric layout forces the team to consider whether the geometric interfaces among the chunks are feasible and or to work out the basic dimensional relationship among the chunks. By considering a cross-section of the printer, the team realized that there was a fundamental trade-off between how much paper could be stored in the paper tray and the height of the machine. In this step, as in the previous step, the team benefits from generating several alternative layouts and selecting the best one. Layout decision criteria are closely related to the clustering issue in step 2. In some cases, the team may discover that clustering derived in step 2 is not geometrically feasible, and thus some of the elements would have to be reassigned to other chunks. Creating the rough layout should be coordinated with industrial designer on the team in cases where the aesthetic and human interface issues of the product are important and strongly related to the geometric arrangement of the chunks. So that is about step 3, create a rough geometric layout. Now we will go into step 4, identify the fundamental and incidental interactions. That is a more detailed step. Most likely a different person or group will be assigned to design each chunk because the chunks interact with one another in both planned and unintended ways. These different groups will have to coordinate their activities and exchange information. To better manage this coordination process, the team should identify the known interactions between chunks during the system level design phase. There are 2 categories of interaction between chunks. First, fundamental interaction are those corresponding to the lines on the schematic that connect the chunks to one another. Second, incidental interactions are those that arise because of the particular physical implementation or functional elements or because of the geometric arrangement of the chunks. So here example will help. For example, vibration induced by the accumulators in the paper tray could interfere with the precision location of the print cartridge in x-axis. While the fundamental interactions are explicitly represented by the schematic showing the clustering of elements into chunks, the incidental interaction must be documented in some other way. For a small number of interacting chunks, fewer than about 10, an interaction graph in a convenient way to represent incidental interaction. A larger system with type of graph become confusing, and an interaction matrix is useful instead and can be used to display both fundamental and incidental interactions. So these are technical, some suggestion how we can plan thing here. We can use the mapping of the interaction between chunks to provide guidance for structuring and managing remaining development activities. Chunks with important interactions should be designed by groups with strong communication and coordination between them. Conversely, chunks with little interaction can be designed by groups with less coordination. So that's all about what are the structured steps one can follow. To create a good reliable product architecture, which will be good for the future, yeah. Now let's discuss something that we might have discussed, a term called platform product or something like that, and it comes in this context also. So platform planning, so basically it's about that a product, so for example, for the particular printer example that we are talking about, so the customer belongs to three market segments: family, student, small office, and home office. To serve these customers, the team could develop three entirely different products. It could offer only one product to all three segments, or it could differentiate this product through differences in only a subset of printer components. A desirable property of product architecture is that it enables a company to offer two or more products that can be highly differentiated yet share a substantial fraction of their component. The collection of assets, including component design, shared by this product is called product platform. Planning the product platform involves managing a basic trade-off between distinctiveness and commonality. On the one hand, there are market benefits to offering several very distinctive versions of a product. On the other hand, there are design and manufacturing benefits to maximizing extent to which the different products share common component. Two simple information systems allow team to manage this trade-off: the differentiation plan and the commonality plan. So first we'll understand what is differentiation plan. The differentiation plan explicitly represents the way in which the multiple version of a product will be different from the perspective of the customer and the market. The plan consists of a matrix with rows of differentiating attributes of the printer and with columns for the different version or model of the product. By differentiating attributes, we mean those characteristics of the product that are different to the customer and that are intended to be different across the platform products. Differentiating attributes are generally expressed in the language of specification. The team uses the differentiation plan to codify its decision about how the product will be different. Unconstrained, the differentiation plan would exactly match the performance of customer in the market segment targeted by each different product. Unfortunately, such plans generally imply products that are prohibitively costly. Now, commonality plan. What is it? The commonality plan explicitly represents the way in which the different versions of the product are same physically. The plan consists of a matrix with rows representing chunks of the product. Third, fourth, fifth column correspond to the three different versions of the product. The second column indicates the number of different types of each chunk that are implied by the plan. The team fills each cell in remaining columns with a label for each different version of a chunk that will be used to make up the product. Unconstrained, the most manufacturing engineer would probably choose to use only one version and each chunk will in all variants of the product. Unfortunately, this strategy would result in products that are undifferentiated. Now, how do we manage the trade-off between differentiation and commonality? The challenge in platform planning is to resolve the tension between desire to differentiate the product and to desire for this product to share a substantial fraction of their components. Examination of the differentiation plan and the commonality plan reveals several trade-offs. For example, student printer have the potential to offer the benefit of small footprint, which is likely to be important to space conscious college students. However, this differentiating attribute implies that the student printer would require a different printer mechanism chunk, which is likely to add substantially to the investment required to design and produce the printer. This tension between a desire to tailor the benefit of a product to the target market segment and the desire to minimize the investment is highlighted when team attempt to make the differentiation plan and the commonality plan consistent. We offer several guidelines for managing this tension. First is platform planning decision should be informed by quantitative estimates of cost and revenue implication. Second is iteration is beneficial, and third is the product architecture dictates the nature of the trade-off between differentiation and commonality. So what that means, the nature of the trade-off between differentiation and commonality are not fixed. Generally, modular architecture enable a higher proportion of component to be shared than integral architecture. This implies that when confronted with a seemingly interactable conflict between differentiation and commonality, the team should consider alternative architectural approaches which may provide opportunity to enhance both differentiation and commonality. Sorry. So that's all about this chapter. Yeah. And as usual, this is the book from where we are I'm giving these lectures, and you can find the link in the description also. So that's it for this week, and then see you in the next week then. Bye bye.